This is Dusty Jones, here to talk about angular measure. The early Greek idea of an angle was that it was a deflection or a breaking of a line. And so they thought of it as one single line that kind of bounced off something or was broken. Euclid, in his Elements, presented a new idea when he wrote that a plane angle is the inclination to one another of two lines in a plane which meet one another and do not lie in a straight line. So we've got these two different lines that cross each other, and then the amount that one is inclined to the other is the angle. Throughout history, at least since the invention of the printing press, various symbols have been used for angles. So you can see what was used in France, England, Germany, and really in 1923, in a very influential report, the U.S. National Committee on Mathematical Requirements recommended the symbol that we currently use as the standard symbol for the angle in the United States. Some different kinds of angles, particularly right angles, I want to talk about. Before we do that, I want to mention a straight angle, which is actually not allowed for in Euclid's Elements, but a straight angle would be an angle whose two lines, or rays that make up the angle, are actually on the same straight line. A right angle is formed by setting two straight lines on each other so that the adjacent, or angles next to each other, are equal. So angle 1 and angle 2 are equal. These angles are called right angles if that happens. And Euclid's Elements postulate 4 states that all right angles are equal to each other. A postulate is something that we're going to take as given, that we're not attempting to prove it. If the sum of two angles is equal to one right angle, or in degrees we would think 90 degrees, we call those angles complementary. If we take two angles and add them up and we get that sum is the same as the sum of two right angles, or 180 degrees, we call those angles supplementary. So you can see angle 1 and angle 2 are complementary because together they make a right angle, and you can see that angle 1 and angle 3 are supplementary because together they make a straight angle. The most common way that you and I know about measuring angles is in degrees, and using that Babylonian idea, there were 360 degrees in a full rotation. For parts of degrees, sexagesimal fractions were used and are still used today. There are 60ths and then 60ths of 60ths, or the 3600ths. Arabic translations of Ptolemy's Almagest called these the first small parts. The 60ths were the first small parts, and the 3600ths were the second small parts. When this was translated to Latin, first small parts became partes minutae primae, and second small parts became partes minutae secundae. And we get our words minutes from minutae, small, and seconds from secondary from these terms. And an interesting quote from Historical Topics for the Mathematics Classroom is this, that the degree or hour, minute, second system is the most popular and least logical systems of angular measure. There are different ways of measuring angles, and some might even say more efficient or even better ways. But degrees, minutes, seconds is very popular. One of these other ways of measuring is with radians. Mathematicians and physicists considered the need for a new angular unit in the late 1800s. This is after calculus has been developed, and scientists and physicists and mathematicians are starting to do things like find the lengths of arcs or areas under curves. And converting to degree measure and then converting back to degree measure was pretty cumbersome. So they settled on a new term, which was a radian, and radians are based on the length of the radius of a circle compared to the arc length of a circle. And it really simplified different formulas. So if we have a central angle, that's just an angle on a circle where the vertex is at the center, and that angle subtends or intercepts an arc of a circle, the radian measure of the angle is the ratio of the arc length of the circle to the radius of the circle. So if we measure the arc length and divide that by the length of the radius, that tells us the angle measure in radians. Really, the radian measure tells you the proportion or percentage of the radius that you're taking up with the arc length. A full rotation, therefore, would be the full circumference of the circle, which would be 2 pi times the radius, so 2 pi radians. A right angle is a fourth of a circle, and so we could take the circumference, 2 pi, divide that by 4, and that's where we get pi over 2. A single radian, if you can imagine laying a radius on that circumference of the circle, it would take up a little bit less than 60 degrees. Now what I'd like to do is just start thinking about different places where we see angles, and one is in the hands of a standard clock. And I'd like for you to answer these questions about the angle that the hands of a clock form at 3:30 and at 4:50. Just as a hint, at 3:30 the hands of the clock don't make a right angle because the hour hand has moved a little bit off of the 3 by the time that we get to 3:30.